Okay, I think we can get started. So, good morning, everyone. Welcome to the GISS Sea Level Rise seminar. We're very glad to have Dr. Jessica Mejia with us. She is an assistant professor of cryosphere and polar sciences in the Department of Earth and Environmental Sciences at Syracuse University, and her research focuses on understanding how water interacts with glaciers and ice sheets to affect ice flow. She uses observational field-based methods, including hydrologic, geodetic, and geophysical, process-based models, and remote sensing to study the structure and evolution of the glacial hydraulic system and the physical processes controlling hydrodynamic coupling on the Greenland ice sheet. Dr. Mejia received her MS in geophysics from the University of Alaska Fairbanks and her PhD in geology from the University of South Florida. And she was also a postdoctoral research fellow in the Glacier Modeling Lab at the University of Buffalo, where she led field campaigns on Helheim Glacier in southeast Greenland. So today, Dr. Mejia will be speaking on the topic hydrology of the Greenland ice sheet, impacts on ice dynamics and sea level rise. So welcome.
Hi, everyone, and thank you, Patrick, for that great introduction and for the invitation to speak about some of my research with everyone today. So as that great introduction said, I'm going to be speaking today about some of my previous work and current work on trying to understand the Greenland ice sheet's hydrologic system. With the overall goal of this work is to understand these processes better, understand the interactions with ice dynamics and that interplay there, and then ultimately to try to constrain sea level rise better as the motivation, I think we all kind of have in this field. So I won't dive too much into, the introduction and details since I think we're kind of all on the same page here with, the Greenland ice sheet is losing mass. So is Antarctic ice sheet, but the Greenland ice sheet is losing mass at an accelerating rate, particularly over the last few decades. Well, this mass loss is typically or is broken into two main components. So we have the runoff component, so that meltwater runoff, and then we have ice dynamic calving. If we look at how the proportion of mass loss from these two processes has changed over the within the last 2 decades or so, we've seen a shift from ice dynamics and ice dynamic discharge being the main mechanism of mass loss to runoff being more and more of a concern. With this increase in the magnitude of melting over the Greenland ice sheet. So this is now it's runoff that is dominating our mass loss from the Greenland ice sheet, and it's expected that runoff will continue to be kind of dominating this mass loss budget of the Greenland ice sheet moving forward in the coming decades, kind of motivating and making just the runoff and understanding our melt even more important and how the ice sheet is melting. So with this increase in runoff, this is kind of being accomplished or kind of has repercussions in a few ways. So we see an increase in our temperatures, we see an increase in the magnitude of melting, but we also see an increase in the melt area. So the area of the ice sheet that is experiencing melt over a given year. So here I have some data that I've combined from a few papers here that is just showing that we have seen an increase in the area of the ice sheet that is melting in a given year over time over the last several decades. So these kind of little insets show the Greenland ice sheet's melt area from 1972 on the left-hand side to 2011, and it look similar or even increases inland for more current years. But we've seen just a dramatic increase in the inland extent of melt on the ice sheet. We've also seen extreme weather events such as rain at Summit Station a few years ago. So the area that is experiencing melt is very important. And with this, we're seeing the inland expansion of the ablation area as well. For example, another repercussion of this is we've been monitoring the inland advance of that ablation area and of supraglacial lake distributions advancing inland. So here are just two figures showing that the superglacial lakes in different regions of the Greenland ice sheet have been retreating inland. So all of this to say that the expansion of this ablation area, this melt occurring at higher and higher elevations over larger areas, just makes understanding how that meltwater is traveling through the glacial hydraulic system even more important. And typically, with especially our larger scale models, we kind of take this, we know it's melting, we take this meltwater runoff value and we kind of throw it into the ocean. And we really ignore a lot of the complexity of that water traveling through the superglacial and glacial subglacial drainage systems, even though these processes are interconnected. So why this is important is because whenever we have meltwater that is produced on the ice sheet surface, it can reach the bed through fractures that can hydraulically propagate, leading that meltwater to the ice bedrock interface, can lubricate that overlying ice and accelerate ice motion. So really creating this coupling between our hydrology and our ice dynamics of the Greenland ice sheet. So making these processes interconnected and really not able to be separated. So the kind of overall goal of big question that I'm interested in is how will the Greenland ice sheet respond to future melt increases? And while I won't answer this giant question today, I will be talking about some of my work, kind of aiming at trying to understand this by focusing on several of these smaller processes that are all interrelated. Particularly the relationship between our future increases in runoff and ice dynamic mass loss from the Greenland ice sheet is still debated. And we really just need to understand the glacial hydraulic system and hydrodynamic coupling in Greenland and in ice sheets in particular to resolve these future mass loss contributions. And to do this, I kind of argue throughout my work that you really need observations. They're just really critical to evaluate what are our assumptions of what is important and what isn't important, so that we can put that in context and really kind of narrow in on what are the most important processes for future mass loss and sea level rise and target our, numerical modeling efforts there. So today I will be discussing some of my work, again, targeting this, starting with some of my work in the Western Greenland ice sheets ablation area. And then if I have time, I'll quickly move on to some of my more current work in Southeast Greenland and the firn aquifer, understanding the melt there. So first, I'll discuss previous work in the Pakisat region of the Western Greenland ice sheet, looking into how lags in meltwater propagate through the glacial hydraulic system. So here, taking a very holistic approach to looking at the hydraulic system, so not just really separating out, oh, here's the supraglacial drainage system, and that's very independent of the subglacial drainage system, but really trying to see how the whole glacial hydraulic system is interconnected and how differences in the timing of meltwater production and delivery to moulins kind of propagate through that whole drainage system there to affect ice speeds and dynamic discharge. And I think my collaborators on this, Jason Gully, Celia Trudes, Matt Covington, Tim Bartholomew's, Charlie Breitup, Sarui Z, and Tim Dixon. So if you were to say that the timing of meltwater delivery to, say, moulins and everything happened very uniformly throughout the entire ablation area, this would mean that when meltwater is produced, it reaches the bed at the same time. It would lubricate the bed at the same time there very evenly and uniformly across the ablation area, and presumably you would have one diurnal speed up event that would be quite strong if there's no regions of the ablation area that are really resisting this flow. However, observations indicate that it is not uniform like this, particularly in past observations by Matt Hoffman, who installed a GPS array in Packetsock as well at multiple different elevations and saw that there was a delay in the timing of diurnal peak sliding. It occurred later and later in the day as you got further and further up glacier to higher elevations. So thinking about what could possibly be causing this, well, we know that there are controls on the timing of meltwater delivery to moulins, and these are typically caused by the size, shape of the supraglacial drainage system or the internally drained catchment. So an internally drained catchment is just the area of the ice sheet that's draining into one moulin. So kind of intuitively, we can understand that. So if you have a very large catchment with many kilometers of superglacial streams, you would expect it to take longer for that water to travel through that larger network and then reach your moulin than it would if you have a very small catchment. The water doesn't have as long to travel, so it can get to that moulin quicker, right? So Larry Smith kind of did a parameterization on many different catchments in Southwest Greenland, kind of showing how this catchment size differences can affect the timing of peak meltwater delivery to moulins or to that moulin that's draining each of these catchment and showing that there should be significant heterogeneity across the ablation area. But there is a pattern to this heterogeneity. So Ken Yang and Larry Smith, some of their past work shows that so moulin density decreases the further elevation you get on the ice sheet or the further inland you get. So if you have a lower moulin density, you have fewer moulins draining a larger area. So your catchments get bigger, they're draining a larger area, and you should have longer lag times between the timing of peak melting and peak meltwater delivery to those moulins. So in this study, we set out to kind of test this, right? So is this the reason these larger catchments with these longer delay kind of superglacial delays in residence time of this water, is that the reason why there have been these observations of a later timing of peak sliding at our higher elevations in Packetsock? Right, so is one area then resisting flow while another area is promoting flow, resulting in this heterogeneous pressurization in the subglacial drainage system, which could ultimately be important for understanding that relationship between meltwater inputs and ice dynamics at the glacier scale. So this work was done in Packetsock in Southwest Greenland. So on Sirmiak Avanyatlak, that's north of Sirmiak Kujala and formerly known as Yakasaben. So this work, here I'll zoom you in really quick. So this work is done mainly at two field sites. So we have a lower camp, a lower elevation site around 800 meters elevation, and a higher elevation site called high camp, around 950 to 1,050 or so meters elevation band. So at these two camps where we identified a main catchment and installed several instruments there. So at each of these sites, we installed automatic weather stations to monitor the timing of peak melting or peak meltwater production across our study area. We then installed stream gauging stations over the highest order stream or the largest stream right near the moulin. So in this bottom photo, you can see we have our stream monitoring station here, and in the background you can kind of see there's the moulin right there. So really right upstream of our moulin, we installed this gauging station, and we want to monitor superglacial stream water level such that when we have peak water level in our stream, we should have peak meltwater delivery to our moulin. We then also supplemented this with by instrumenting moulins with piezometers to monitor moulin hydraulic head or moulin water level, which gives us the timing of the peak pressurization within the moulin connected subglacial channelized system. And finally, we installed several GPS stations around each site so we could monitor the timing of peak sliding speeds. Okay, so here isn't kind of looking at this first kind of lag time here. So lag time between peak melting and peak meltwater delivery to moulins. So we have our two main catchments, our low camp catchment, Jamay, which was only 0.24 square kilometers, like a very small area, whereas our upglacier or high camp main catchment, radical catchment, is almost 17 square kilometers. Has an area of almost 17 square kilometers. So quite significant areas that they're draining there on the ice sheet. This figure is also showing some supplemental observations we took from two other intermediate catchments, one at low camp and one at high camp. And we can see here on the left, I'm plotting meltwater delivery lag, so the timing between peak melting and peak meltwater delivery or peak stream stage in each of those streams versus drainage basin area. And we can see this relationship here where we have a larger catchment, we have longer lag times. And then on the right-hand side, we can see all of our diurnal stream stage observations plotted on top of each other for all of our different observations over the 2017-2018 melt seasons. So the pink lines correspond to our low camp, so our smaller catchments, and our blue line corresponds to our larger catchment at Radical. And here we can see that we have a later timing of meltwater delivery at our larger, higher elevation catchment. In particular, on average, our high camp station was recording that we have peak meltwater delivery to moulins 4 hours later than at our lower elevation stations. So here we do see a significant difference in the timing of meltwater delivery to our moulins, which we did expect. So now I'll put this data with some of our other data sets here. So we have our on the top, we have our timing of peak meltwater production, which was uniform across our two stations, occurred around 1:30 p.m. local time. Then we have our moulin input, so that's that same discharge into our moulin, so our stream stage there. Now looking at our moulin hydraulic head and our ice velocity. So on the left, we have just the time of day, and on the right, we have the same data just shown in our lag times from peak melting. So that difference between the timing of peak melting to each of these two things. So we have first our peak meltwater production, then we have our peak meltwater delivery to our moulins. At our low camp site, we see that that is occurring about 4 hours earlier in the day than at our high camp site. We then see about a 2-hour lag between the timing of peak meltwater input to our moulin and peak moulin head. So a difference in that timing to peak pressurization of our subglacial channel that's connected to that moulin. And we see a difference between these two sites of 1 to 3.25 hours, which is mainly caused by that difference in the timing of that meltwater delivery to the moulin. So that's a strong correlation there. So timing of our peak pressurization is really controlled by the timing of meltwater delivery to that moulin, which makes sense. Okay, finally, then if we look at our peak sliding speeds, we see something interesting. So at our low camp site, which is in these red colors, peak diurnal ice velocity was basically coincident with our peak moulin head, so our peak pressurization of the subglacial drainage system, which again is what we expected, right? When you have peak pressures, you should have peak sliding there. And that's what we see. However, at our high camp site, we see a significant lag between the timing of peak moulin head and the timing of peak ice velocity. That is not just accounted for by those supraglacial meltwater routing delays. Ultimately, we have a difference in the timing of peak sliding of 2.2 to 7.6 hours between our two sites. So peak sliding is occurring much later in the day at our upglacier site. Okay, so that was kind of a synthesis of all the data. But if we were to look at this data, same data as a time series, here we can see the same order. So we have our melt rate at the top, our stream stage, moulin water level, and then our ice velocity with the orange colors denoting our lower elevation sites, our smaller catchment, and then the blue indicating our high campsite. So from this, we see that one, our supraglacial residence time, so meltwater in these larger catchments, is delaying meltwater delivery to moulins. We see that because of these superglacial routing delays, moulin water level is peaking later in the day at our upglacier sites than they are downglacier. So this is resulting in this non-uniform subglacial pressurization where we have some areas that are experiencing their peak pressurization at different times than other locations based on those superglacial characteristics. And then finally, we have our peak sliding that is again occurring earlier in the day at our downglacier sites, later in the day at our upglacier sites because of this timing of peak pressurization. However, at our upglacier site, at our higher elevation site, peak sliding is not coincident with peak moulin head. So ultimately, this indicates that the lags in the timing of meltwater delivery at high camp, they did not entirely account for that timing of peak ice velocity. But at our lower elevation site, they did, right? So it was more what we expected. Our kind of interpretation of this data is that at our higher elevation site, there are some non-local controls on sliding, right? So at our lower elevation site, you have the timing of peak pressurization, you have peak sliding, so you're very locally controlling that like hydrodynamic coupling relationship, whereas at our higher elevation site, there are some non-local controls, which could have been resulting from the timing of pressurization in other neighboring catchments that were occurring at a later time, therefore resisting flow while our moulin was experiencing its peak pressurization. So here it could be a balance between the timing of our peak moulin pressurization across our larger area where there are fewer moulins and they are larger, so there are larger delays. And this kind of theory is kind of supported by just the moulin density if we look at our two areas. So on the left, we have our low campsite where we can see all these different colored dots indicate the locations of moulins in either 2017 or 2018, and the red lines are crevasses that have recently formed over that year. So at our low campsite, we have over 10 moulins per square kilometer. So that's our moulin density there, whereas we have a much lower moulin density at our high campsite with only 1 to 3 moulins per square kilometer. And just looking at these two figures here, you can see that there are many fewer moulins at our higher elevation site, which could have been responsible for those non-local controls on sliding because such a much larger area was resisting flow while we experienced our peak pressurization. So the key takeaway from this is that moulin density controls the timing of peak pressurization, or is controlling the timing of peak pressurization within the subglacial drainage system, and also moulin density, particularly at our higher elevation sites, is responsible for some of these non-local controls and coupling. So the moulin density just of an area is just very important, right? Because it's controlling our catchment size, those lags in the timing of meltwater delivery to our moulins, but then also is influential in our hydrodynamic coupling relationship there, local versus non-local controls. So the next thing I'll discuss is some of kind of focusing on the supraglacial drainage system and looking at interannual variability in the Greenland ice sheets internally drained catchments. So, like I just said before, the size of these supraglacial catchments is very important for the timing of meltwater delivery to moulins. And that's the main control there. So the size, shape, and locations of internally drained catchments are thought to be generally static. This is because on large scales, bed topography transferred to the ice surface is responsible for our ice surface topography. So we have where we have troughs, we have depressions at the ice surface and vice versa, and then crevasses are open in the same regions of extensional strain as the ice sheet is flowing over those same bed perturbations. And that they should either effect downstream and then reopen in the same location over and over again. So from this reasons it's thought that the internally drained catchments are basically static. However, this is all coming from the assumption that, supraglacial streams generally adhere very well to this large stream ice surface topography. However, as we know, supraglacial streams will thermally incise into the ice as they flow. And this is quite variable depending on your location, but can be quite significant. And supraglacial streams have been observed to breach topographic divides or drainage basins previously in Greenland. So if an internally drained catchment were to vary on interannual timescales, this could happen if the largest or the highest order superglacial stream is going to deviate from our large scale ice surface topography. So even though a very small proportion of a superglacial catchment will deviate from our large scale flow, if this occurs over the very critical highest order stream that is leading to our moulin, then we can get some interannual variability there. And that's where these very small order changes or this very hyper localized surface topography could really be important at the larger catchment scale when we're looking at our superglacial catchment distribution. So to investigate this, I'm focusing here on 3 superglacial catchments that were at our high camp site. So here only focusing on our high camp site. So on the right-hand side, you can see a zoom in of our 3 catchments where we have radical catchment that I just spoke about on the right. And then we have 2 other smaller catchments, Mars in the middle here, draining a quite large superglacial lake. And then we have our Arksov catchment draining another smaller superglacial lake into a moulin. So I looked at the distribution of these catchments over 2017 to 2019 and saw that over this time period, they coalesced. So here I'm going to break down some of the observations of how this occurred. So first, radical catchment in 2017, so the same figures on the left. Here we can see the highest order superglacial stream plotted here in purple to orange shading, and then an inset showing that elevation profile with red indicating all the areas along the stream's flow path where it was flowing counter to large-scale topography accommodated by thermal incision at the base of the stream, allowing it to still flow downslope at its base, but again to counter large-scale ice surface topography. The purple dots here indicate a topographic high point, and the orange indicates a topographic low point. So here we can see that it flows out of the superglacial lake basin on the right over a very short superglacial high point, then downslope for most of its length until it kind of gets out of this catchment near this orange dot, kind of meanders and then flows downslope into radical moulin in 2017. Okay, so now looking at Mars and Arksov catchments here on the left, I'll zoom you in to how they are draining from these lakes into moulins. So here we have Mars Lake on the right and Arksov Lake on the left on the bottom here, just kind of cropped, so we can see their drainage paths. The stream is outlined in blue, and then our transect, so where we were monitoring using a differential GPS survey, we walked along that the ice surface right next to those thermally incised channels to monitor the ice surface topography along their flow. So here we have our elevation profile along Mars Lake, where we have from our shoreline on our right to the moulin on the left with that blue triangle. So along this transect, we can see that the superglacial stream thermally incised through a very large ridge that is 11 meters above the lake shoreline at the time of mapping. So quite substantially. And there's location right there in the middle of our topographic high point. And here's just some photos showing the transect where we're walking very clearly uphill along this. And we can see how deeply thermally incised the supraglacial stream is. We can see some collapsed snow bridges indicating that this flow path was reactivated in 2017. So it likely flowed along this in the previous year, melted through that channel again at its base, and then that snow plug had collapsed afterwards during the 2017 melt season. Here is a photo of Mars Moulin. There was no slopes, no snow plugs were visible on the Moulin, indicating that this was a very fresh Moulin. You can see all of the grooves in the ice indicating past stream stage levels during the draining process. And it was quite fresh. It had drained in the 2 weeks prior to this photo being taken in 2017 melt season. So Mars Lake, it drained through this basically a supraglacial canyon that was 11 meters high. Arksov Lake, on the other hand, here's the elevation from the shoreline on the left now to the Moulin on the right, again indicated by this triangle. And we can see here that the stream thermally incised through a about 3-meter vertical difference there to the Moulin, between the Moulin and the shoreline at the time of mapping. And here is a photo of Arksov Moulin. You can see the roving survey in the background, but Arksov Moulin was snow plugged, which indicates that it was an older Moulin that had formed at least the previous year. Snow formed over the winter, and then it was reactivated again this year. So that this Moulin was older. And here you can see another snow kind of a snow bridge kind of on one of the walls here overhanging over this stream, as it is incising quite deeply down to get to that Moulin. So summarizing our 2017 observations, the deeply incised supraglacial channels draining both Mars and Arksov lakes allowed the stream to flow against large-scale ice surface topography. And this uphill flow allowed these lakes to drain into moulins that were located outside of their local drainage basins. And importantly, Mars Lake appeared to drain through the same canyon incised during the previous melt season, and Arksov Lake at least seems that it intersected an older stream that it flowed through the previous melt season, because we saw those snow plugs only at the end towards that moulin. Okay, so here is what the catchments look like in the 2017 melt season. We see some variability in the coalesces of our Mars and radical catchments in 2018. And let me plot this here. So instead of draining back into radical Moulin, the radical river that was draining into radical Moulin and draining the basin instead breached the topographic divide, separating it with Mars Lake, drain into Mars Lake, and then Mars Lake, instead of draining back into the same Moulin, breach another point on the drainage divide and flowed into a new Moulin. So these two catchments coalesced, creating a very large catchment that was over 28 kilometers square. So quite dramatic here. So zooming in on this radical and Mars catchment merger, here I have the elevation, again, inset showing Radical River from where it exits Lake 41 here on the right until where it enters Mars Lake. And again, all of the red is showing where it is flowing counter to large-scale ice surface topography. So we see that between the topographic low point and the topographic high that separate Mars and Arksov Lake, we see that the stream is flowing counter to what we would predict if we just use large-scale ice surface topography alone. So now I'm going to show some ground observations to try to deduce what was the cause here. So at the intersection between Radical River, where it started to divert from its flow previously, we see just a very long snow-filled intersection. So here on the left, you can see Radical River. It's flowing towards the camera, a very slushy interface, snow filling that the channel that had formed the previous year, and then basically this snow plug that formed there, completely blocking off access to Radical Moulin. And this length scale is about 200 meters. So such that even if a new crevasse were to open there in the same exact, coordinate locations as it had been the year before, or if Radical Moulin could have stayed open, that wouldn't matter. That this snow plug itself was preventing the river from flowing into that moulin. So not a case here of an ice dynamic or a crevasse opening reason why we don't have flow into this moulin, but we have this snow infill of this incised channel instead that has been diverting this flow away and causing it to flow over another drainage basin. So here we have, if you look at D, E, F, and G, so the bottom four of these photos, you can see what it kind of looked like on the ground. So it's very gently sloping, a very wide supraglacial stream here that is, quite wide. We have some kind of islands that have formed in the middle as this river is trying to flow and meander over that topographic high point. On the top right, you can see a satellite imagery from WorldView from the early 2018 melt season showing just how wide this river is. And you can see in red that old superglacial flow path to Radical Moulin, but instead we kind of follow around that contour going further and then breach this topographic high that is again shown in that purple dot. And then after that point, the stream then flows quite steeply downslope into Radical River, or into Mars Lake, sorry. And then in 2019, the stream followed this new flow path. So it did not flow into Radical River or into Radical Moulin again. Instead, it again flowed into Mars Lake. I interpret these observations as the snow plug diverting stream flow. So we have over winter snow infill. We have a snow plug that has formed when it's trying to be reactivated. If water can't melt through the snow plug fast enough, it will instead collect in whatever surface depression is there at the intersection. And it really then becomes this rate of snow plug melt versus how big that depression is and how quickly that is infilling. If we fill this kind of surface depression too quickly or much faster than we can melt through that snow plug to try to get back to that same moulin or that same area of extensional strain, then we can have a small spillover event that will then thermally incise a new meltwater path. And particularly this would be cause the most interannual variability in your catchments in areas where you have, in general, gently sloping surfaces. Because if you can imagine, if we had a very strong surface gradient, then we can just kind of form that stream right back to the same moulin if there is no other area where we can have a very large significant change in that flow path. Here's just a photo here of Radical River now emptying into Mars Lake here, and ultimately resulting in the diversion of the flow path and the reduction in our moulin density of the area because there are so few to begin with. So now we're removing another one over a large area. Okay, looking at Mars and Arcsov lakes, we can see that Mars Lake, it did not reactivate that same flow path again in 2018. Instead, it breached a new a second highest topographic high point north of the old channel. Sorry for, I hope it's not too loud for everybody. They're doing some yard stuff outside. So it breaches a new high point. So it didn't melt through this old snowplug channel like it did the previous year. So here's this intersection, right? So where it looked like it was trying to melt through that same snow plug channel again, which would have been at least the third year. But instead, it had breached a higher topographic high point, incised a new flow path to the north of this old channel, abandoning this snow-filled old channel. So you can see here a collapsed snow bridge, but you can see some turbulent scallop marks on it, indicating that water was kind of like sucked out of this as the lake drained and dropped its water level. So here's just some photos showing this new flow path with these very fresh features, in stark contrast to the previous year with our snow bridges. So we have a lot of fresh overflow features as it drained through this canyon that it formed. So here, if we look at the elevation data along the transect, and here on the left, we have just a map showing some of our surface elevation contours. So we see it did breach a new higher location on the same topographic divide, which ultimately resulted in us diverting flow to a new moulin, Phobos Moulin, which is further downstream than Mars Moulin. Arksov Lake, on the other hand, so instead of flowing back into and reactivating the same drainage path as the previous year, instead it flowed into Mars Moulin, so the one that drained Mars Moulin the previous year, kind of reforming a flow path very parallel to that old flow. In 2019, as you can see here, Arksov Lake did not flow into either Arksov or Mars Moulin. Instead, it consolidated and flowed into Phobos Moulin again. So resulting in 2019, Phobos Moulin, this one moulin, draining this entire area that used to drain these three catchments. So altogether, these observations are highlighting the importance of very small scale localized surface topography on large scale supraglacial catchment size, shape, and the number of them in an area, particularly at these higher elevations where surface slopes are generally much more shallow and kind of allow for these things to occur. In 2018, for example, we moved the point source, so where water is actually getting to the subglacial drainage system, moved it by 3 kilometers, which is quite significant. And again, we lower the moulin density in the area. So going from 3 moulins in this area in 2017 to only 1, and really concentrating that flow and really growing the size of these catchments. So this should be important, particularly where we have areas with shallow slopes, such as at these higher elevations. So as our melt is expanding inland and our superglacial lakes are forming further inland where our surface slopes are more shallow, this can be, I would suggest it would potentially be more of an issue. So maybe to not assume that they are all going to be static, but implement some type of classification or variation and explore the possibility that these catchments can change in size year to year. I don't have too much time left, but I'll talk briefly about some of my other work focusing on the subglacial drainage system, using rapid superglacial lake drainages kind of as a probe for subglacial drainage system conditions. So the classic conception of the subglacial drainage system's evolution is that you have meltwater inputs to the subglacial drainage system in a moulin in the beginning of a melt season. It's very inefficient, causing pressurization at the bed, and then you'll eventually have a speed up. As that drainage system, particularly our subglacial conduits that are connected to our moulins, as they grow and they increase their hydraulic capacity, it's thought that then they can accept more water, route that down glacier more efficiently, and then that will kind of drain water from the surrounding area to lower ice velocities, right? And it's like this all centered around the growth of these subglacial conduits and their ability to grow over a melt season that is responsible for this seasonal slowdown in ice velocity, with the theory basically derived on alpine glaciers and then applied to the Greenland ice sheet. Once we saw that, we do see a seasonal pattern where we have an increase in ice velocities in the summer and then they decrease during the melt season. So in 2017, now looking at our low camp site, it is conveniently downstream of the subglacial flow path of many supraglacial lakes upstream. And we were able to detect a supraglacial lake drainage of all of these different lakes upstream. So here, if we're looking at our Moulin hydraulic head, glacial hydraulic tremor amplitude, which I'm not going to discuss much about, and then ice velocity. The important things here is that there's a big spike in the middle here where we have a giant increase in our hydraulic head, and then we see a very significant increase in our ice velocities or our sliding speeds. And that was caused by this lake drainage event that occurred many kilometers up glacier. The subglacial flood wave drained past our site. So we captured that with our moulin. So we see that spike, we see this increase in ice velocity, and then we see a subsidence, and then go back to our diurnal signals after that, because this was occurred in late July. So from this lake drainage event, we see a modification of our characteristics of our relationship between our moulin hydraulic head and our sliding speeds. So before the lake drainage event, we have on the bottom this red line indicating our winter time background speeds. So before that, our minimum sliding was always above this threshold, whereas we see an abrupt shift after this lake drainage event where we've reached these wintertime background speeds, and then we recurrently achieve these speeds again. However, we don't see a change in the relationship or in hydraulic head in our moulin, right? So if it was the growth of these subglacial channels that was responsible for this decrease in ice velocity, we would expect to see a lower moulin hydraulic head. So lower pressures in the drainage system that are then correlating with whenever we see these lower sliding speeds. But that's not the case. We see lower sliding speeds without a change in our channelized drainage system. So we interpret this instead as, no, there are more built here. We interpret this following Lauren Andrews' previous work on the weakly connected or isolated component of the subglacial drainage system, whereas we have many hydraulically inefficient or disconnected or weakly connected parts of the subglacial drainage system, so the link cavity system. Before we have our lake drainage event, we then have this flood wave that arrives, really throws water up throughout the whole subglacial drainage system and injects it over a large area, because we also have this very strong uplift signal here. So we're lifting the ice sheet off its bed, injecting a lot of water through this, kind of disturbing this whole system, putting it back down in now a new location, and then we're adjusting to that new kind of state. So this flood wave should have connected these previously disconnected or weakly connected parts of the subglacial drainage system that then stayed at these lower pressures after the lake drainage event. So what's important here is that this is just more evidence for it not being the increased efficiency or the growth of these subglacial channels that are connected to our moulin that are responsible for these seasonal slowdowns in sliding, but instead it is these inefficient, isolated, or weakly connected components of the drainage system, which are actually more important, which is really the opposite of the case as in alpine glaciers. And this is extremely important for understanding how the ice sheet will respond to future melt increases, because our knowledge about changes in the relationship between meltwater inputs and changes in the connectivity of these weakly connected components is not fully resolved, and they don't respond the same to future melt increases with their increasing capacity to just kind of accept and accommodate all of the future melt we would put into the system. Instead, that can change that relationship. So really indicating that we need more work to be done on understanding exactly how the subglacial drainage system is responding to melt inputs and what is the actual mechanism for our observations of seasonal decreases in ice velocity that have been classically attributed to growth in subglacial conduits without direct observations of that. Okay, I didn't get to some other work, but that is fine. Just modeling some of these rapid supraglacial lake drainages. But so I'll end it there. So we have time for questions.
Thanks a lot, Jessica. Do we have any questions? Actually, I'm wondering, could you talk about that modeling work a little bit? That sounds
Yeah,
interesting.
of course. Okay, do you see my screen again?
Yes.
Yeah, so in collaborating with a few colleagues, so Tim Hageman at University of Oxford, and Ravi Deru at Vanderbilt, and Emilio Pania at Oxford as well. We were working on a supraglacial lake drainage model that would be able to very in a lot of detail model this hydrofracturing process. So including melting, frictional heating, turbulent flow, freezing, conduction, but then also including the ability to explore a viscoelastic and elastic fracturing response to a lake drainage event, even on the short time scales that have been involved. So typically, traditionally, it's assumed that glacial ice will just respond purely elastically on these short time scales, right, of a lake drainage event, which is only a few hours. But this model instead incorporates a viscoelastic component. So here's just the model domain for this. And in our simulations, we use some data from Das et al. And their observations of the drainage of North Lake. So here's a simulation showing our surface uplift, and then on the bottom we have our model showing our deformations in our, including a viscoelastic rheology. So here we have our water hydrofracturing to the bed and creating this kind of blister that is uplifting the ice. And we basically see from this that including a viscoelastic component rather than a linear elastic component matches much better to observations in our model. And what I'm excited about here is that we have the ability to more accurately understand the crack width, the crack length, and the subglacial blister that I hope to apply to other lake drainage events and hopefully connect it with a subglacial flood wave so that we can kind of model that full process and try to see what is the full area of the bed that is being modified during a lake drainage event. Since it is so important for changing the structure and evolution of the subglacial drainage system.
That sounds great. We have a question from Jeff.
Hi there, thanks for the talk. The guys at Cardiff University in the UK have developed this instrumented egg, which is supposed to go through the channels and then down the moulin, and then through the subglacial channels as well. And they found that the moulin themselves aren't vertical; they go through all sorts of horizontal movement as well. So you get waterfalls effectively going into pools, and the egg will get stuck in this swirling pool internal before getting out and going to the next level. But they found that the channelized subglacial flow starts quite quickly.
Mhm.
And they, because the egg, the instrumented egg couldn't get out unless there was a channelized flow, and they could trace it all the way to the sea. But have you considered doing anything like that?
I would love to. If So the areas where I'm working or where this study was, the ice is 500 to 800 meters thick. I haven't looked in the past year, but I've been keeping up with that study because I think it's just so neat, the, cryo egg and being able to kind of deploy those in a lot of moulins and kind of actually track where exactly they are. It would be such a great tool for confirming our model and our subglacial routing models, which we know are not all that accurate because, all of the assumptions we make. Do you know if what the maximum ice thickness that they have been able to use them with is?
I think it was about 700 meters.
Oh, they have? Okay, so then they
Yeah.
have been able to use that. I mean, I would love to use that because we do, there is definitely a channelized system underneath connected to our moulins. So I'm not saying that that's the case, that there's just no channelized system. It's just that the relative importance of it is different than what the traditional kind of assumption is. Interestingly, whenever we're instrumenting the moulins, we encountered many of those plunge pools as well that you were describing, where the egg would kind of get trapped and spun around. So that was probably the most challenging part about instrumenting the moulins and trying to get deep enough, is that we would keep on hitting these plunge pools where it would just stay there, and then we would have to wait for it to hopefully melt out after a few days. So it was a lot of like lowering it and trying to catch it in the water to try to get it to kind of go over those different plunge pools. We originally thought that only those plunge pools would really be a problem on a older moulin, but we found that they develop quite rapidly, even if it's a brand new moulin. So we still had trouble with them, even if it was brand new. But that is definitely a challenge there. And Celia Truntz, I mentioned her throughout the talk, and she's a co-author on this. She did some interesting modeling work on exploring the effect of different moulin shapes on the water pressure, water levels within those moulins and on subglacial drainage development, which I think was really interesting.
Yeah, thanks.
Yes, Johnny has a question.
Hi, Jessica. Hi, thanks so much. Those spectacular observations, and you look closer at the surface, and then it's more complicated than you would think, right? And that's good.
Like everything, right?
Like everything, I guess. And so this thing of um, channels flying across larger scale topographic divides, how much do you think is that the cause of that? How much of it is the lake filling and overtopping the lowest sill and then incising? Um, and how much of it is channels being incised and then infected with flow, like maybe sideways, and so they end up in a position
Mhm.
which looks incongruent with the, large scale topography or some other
Yeah.
process. I don't know.
Yeah, great question. So I guess what's kind of was interesting about our kind of the catchment geometry, which was not intentional, I think we kind of got lucky with it, was that just with the orientation of flow. So we had our Arksov Lake, which was the smaller of the two lakes, and that one was flowing very much perpendicular to the flow direction. So with that one, the ice was advecting that old stream downstream, and then a new one would open in the same kind of latitude, longitude coordinates again, right? So it was being abandoned because of advection of that stream to a higher elevation, right? With our Mars Lake, which was that very large lake, um, the ice flow direction was kind of along parallel to those streams. So for that stream, I think that was very much this competition between the rate that it can melt through that old snow plug versus the rate of lake infill, that then it will then reach a new topographic high point and then flow and incise a new channel. So with Mars Lake in particular, it was not our ice dynamic. It was really inflow. And I think what really precipitated it to breach a new high, like the second highest point on the divide, was the consolidation of Mars catchment with our radical catchment. So that effectively tripled the area of melt into that one lake between 2017 and 2018. So maybe if, that radical river didn't breach the topographic high and now have this giant river kind of also emptying into Mars Lake, maybe it would have, the rate of inputs to that lake wouldn't have been enough for it to breach that second higher location, and it would have just melted again through that snow plug. But I think it's really like that interesting there is like the competition between these two processes. Like how long does it actually take to melt through the snow plug versus, that lake infill, and when it just becomes easier to now just increase that lake level to a new higher point.
Mm. Oh, that was going to be my follow-up. Like, how long does it take to melt through a snow plug? Just order of magnitude. Obviously, it must take
I mean,
days.
it can definitely do it in less than a month.
Mm.
Yeah, so in 2017, it probably started to drain in before we got there in the end of July, so a month or two. I think it was probably trying to melt through it.
Okay, for a long time. Yeah, amazing observations, I think.
Any other questions? I guess we're
If there's no follow-ups, I guess one thing to respond to Johnny, like it would be really interesting because I know that you have your modeling of this breaching of a topographic divide and incising a new channel. It would be interesting to incorporate if we could figure out a time scale for snow plug melt, like put that competition there. I've been thinking about that for a while.
Yeah, because I just implemented it, just imagining there was a snow plug which just on T=0 just collapsed. But yeah,
Yeah,
there's that race there, which is not in which the physics of which are not in there at all, like you say. But it could be cool. Could be interesting.
yeah.
Jeff has another question.
Yes, one of the interesting characteristics of the subglacial flow is it forms these at the marine terminating glacier, it forms these plumes of fresh water that come up, and that sort of implies that it must be quite channelized because these plumes are quite localized rather than spreading in general across the glacier front. So you're sort of suggesting that it's sheet flow rather than channelized flow. Is that
So I think that they coexist. So I think there's definitely channelized flow all the way up at our higher elevations where we were. It's just the relative importance of the two that are coexisting at the same time. Because the ice is just so thick when you get upstream that the timescales for this creep closure of our channel is so short that it's really not maintaining its efficiency to a dramatic extent more than a few hours. It's really kind of coupled to the Moulin input cycle.
Yeah, okay, thanks.
Okay. Well, I guess if there are no more questions, we can stop there. So thanks again, Jessica.
Thanks. Thanks, everyone.